Rn, the set of Rn, along with different type of norms that we can measure the size of elements in Rn. Now we're going to talk about different concepts such as open sets, closed sets, boundaries, and interior, that kind of stuff in Rn. The first concept is open set. And how do we define open set in Rn? I mean, open set in R1 is easy. It's just open interval. For example, okay, it can be a little bit trickier than that, but our open interval is one typical example of open set in R1. So how does open sets look like in Rn? So a set V is said to be open. Open, okay, here's what it means. If and only if, give any point in V, there is a epsilon such that you will be able to sketch a little ball centered at A. Remember, this is notation for a ball with radius epsilon. So that this tiny ball, okay, this tiny ball is going to be part of the set V itself, completely inside V. All right. So here's a typical example. So here is a set in R2, okay, it says in R2. So meaning all the points inside is part of the set V, but everything on this boundary here is not part of it. So you pick any point in V, take this guy called A. You will be able to sketch an open ball, as we know, that maybe look like something like that. Okay, it can be tiny enough so that this open ball is inside V. So all the elements in this open ball is also in V. All right. So this is how open set look like. But if you say, hey, the V will also include everything on the boundary here. Okay, if you say V also include everything on the boundary here, then this condition is violated because there may be a point A where there's no epsilon such that this open ball is completely inside V. See, part of it will be outside V. Okay, so this guy is not open. Okay, not open. Closed set. So we define closed set. Use the complement. Closed set. V is closed if its complement is, that's right, open. So the complement set, which is denoted by VC here, is defined to be everything in Rn except elements from V. Okay, so just subtract V. So that's how we define open sets and closed sets. Followed by interior and closure and boundary of a set in Rn. Interior, closure, and boundary of sets. Geometrically, it's pretty easy to visualize all those concepts, so it's a lot easier if you can make a few sketch. But here's we try to define this a little bit more rigorously. A random set in Rn. What is the interior? The interior of V. Here's notation for it. I put a O here. It's defined to be interior, all the x in V. So this is all the x in V, such that there is an epsilon where the ball center at this point is part of V. So that'll make this an interior point. Okay, interior point. All right, let's say if this is V here, okay? You see, if this point right here will be part of the interior point. This guy right here, because you will be able to sketch an open ball with a small radius and this whole thing is inside V. So everything inside here, but not those guys. See those guys? Those guys are not part of the interior, because there's no, doesn't matter how small you pick your epsilon, this open ball is not going to be part of V. Okay, it's not going to be part of V. So in other words, if you get rid of everything on the boundary here, so this is pretty clear geometrically, that's the boundary here. So everything inside, that's your interior. Okay, interior. Next, we talk about the so-called accumulation point, and this will be a rather important concept. As you can imagine, this will be related to the limit, okay, to the limit. A point, okay, it's not. Accumulation point. Accumulation point, of course, of a set V, okay? If every open ball centered at S0 contains at least one point of V, other than S0 itself. Okay, accumulation point. So here, let me make up an example like this, okay? So this is the boundary of the set. Everything inside, okay, there are a lot of points in here, along with this guy and this guy. So everything inside here, okay, everything inside here, along with those two guys. All right, that's my V, okay, that's my V. Let me show you that this, anything inside, that's gonna be accumulation point. Anything on the boundary here, that's also an accumulation point, okay? This is accumulation point, this is accumulation point. The reason is trivial. Doesn't matter how small you sketch that open ball. You see, this guy contains at least 1 point of V. That's not S0 itself. That including this guy, you sketch, doesn't matter how small you make your ball, it'll contain at least 1 point of V. That's not other than S0 itself. Those 2 points, however, these are not accumulation points, okay? Those two guys, not accumulation point. Because it's not true that every open ball centered at this guy contains at least some other point of V. You see here, I can make an open ball that contains only S0, okay? Contains only S0. I can make an open ball that contains only S0. Accumulation points, not accumulation points. Is that clear? So next so this is the accumulation point. We talk about interior. Now let's talk about the so-called closure. Okay, closure. The closure of V. The closure of V, denoted by V bar, it is essentially just the combination of V. So V itself, everything in V has to be in here. Okay, so that's closure of it, combined with all the accumulation points, where V prime represents all accumulation point. With the previous example, you see this is the V here. It's everything inside along with those 2 points. The closure will be all the accumulation point that include everything on the boundary here. Those 2 points, those are part of V, and everything inside. That's the closure, okay? That's the closure. All right, closure. And then we talk about the boundary. What's the boundary? How do we define, say, a boundary point, the boundary of this set? Such that every open ball center at those points, okay, contains all the points such that every open ball centered at those points contain points of both V and, okay, guess what's back there? You see that obviously is the boundary here. So you pick a point on the boundary. The open ball will contain both points from V and also its complement, okay, and its complement. Complement of V, which was denoted by VC, okay? So if I must introduce some notation for this, I can call this, okay? So up here, the closure is defined to be V with all the accumulation points. The boundary of a set denoted by like a partial derivative sign, the boundary of V is denoted to be, let's write down what we just said here, okay? All the x in Rn such that for any R, okay, for every open ball, for any radius, the ball centered at X intersect V, okay? Intersect V is not empty. So in other words, has points from V. And also the intersection between the open ball and its complement is not empty either, okay? It's not empty either, okay? And then we define those points to be the boundary. So now I'm going to show you some example. Geometrically, it's very easy to identify all those concepts, okay, all those sets. So here's the set in R2. X is between -1, Y is between negative x-apps value and positive x-apps value. Let's try to visualize this and then try to sketch the so-called interior and closure, okay, interior and closure. X is between -1. You have x-apps value, and negative x-apps value. This is negative x-apps value. The y cannot be along those apps value functions. All right. That means you have to exclude those points. Exclude those points. X can be -1. X can also be +1, and then everything in between. So if you carefully think about this, it is this line segment without those the endpoints. It is this line segment without the endpoints, along with everything inside. But I have to cut off those parts because there's no equal sign here. Okay, there's no equal sign. So that's what V is. If you consider the concepts that we introduced, it's very easy to write down the interior sketch them as well. Interior. Interior refers to all the points where there is a tiny ball that's completely inside the set. All right. So if you think about that, interior, I can quickly sketch it. You see, this is clearly the boundary here. Okay, it is just everything inside. If I must write down some inequality to describe it, I can do that as well. So all the x and y. X is strictly between negative and 1. See, I have to remove those two boundaries. Y is between those two absolute value functions. That's the interior. Boundary. Boundary, okay? The boundary consists of the points where open balls has points both from V and its complement set. So if you think about that, that's actually, well, those edges, okay, those edges, those straight lines. Boundary. You can introduce equations for it. X is positive or negative 1, and y is between negative 1 and 1. So that refers to those two bounds. Union, all the x and y, such that x is between negative and 1 and y equal to x absolute value and also negative x absolute value. All right, so that's the boundary. I guess you don't have to write this whole thing down, but it's pretty clear that's the boundary. How about the closure? Closure. All right. So leave this to you guys to think about. Okay, closure is everything inside along with everything that's on the boundary. Okay, that's the closure. So you go ahead, write down everything. Okay, go ahead, write down everything that's on the graph here. So that is those two vertical lines. Okay, y is between negative x and x. So negative x absolute value and x absolute value. That's the closure. So finally, let me go back to this graph here. I identified the so-called accumulation points. Accumulation points. I want you guys to think about that. This point right here is an accumulation point because any tiny open ball has an element from V. This on the boundary here is also an accumulation point because any open ball has another point from V. So are those guys, okay? So if you talk about the accumulation point, it's basically everything that you are looking at here, along with everything inside as well, okay? These are all accumulation points. These are all accumulation points. And this wraps up the basic topology of Rn. Now, obviously, we have more properties if I want to talk about it, but I don't necessarily think that's important. But I'll briefly mention about those, okay, in case some people are interested in this. That'll be the focus of some topology course, for example. So right now, this is a theorem, but we are not going to prove it, okay? We're not going to prove it. Like I said, if you're interested in this, you can look that up. For example, we have two different sets, A union B, and we're trying to write down its interior. What do you think the interior of A union B is? And how does it relate to the interior of A and combined with the interior of B? Are they equal or not? Turns out the right property is this is a subset of this. the intersection of A and B turns out equal to the interior intersect B interior B. The closure of A union B turns out to equal to the closure of A intersect the closure of B. A intersect B, the closure of this, turns out to be a subset of A intersect B. Sorry, I don't think this is right. This is wrong. This is actually the union here. Okay, this is actually the union. Number 3, the boundary of A union B is a subset of the boundary of A combined boundary of B. It's a subset. And this kind of it's a little bit kind of trivial. If you consider those two sets, this is A and this is B. The boundary of A, okay, that refers to the boundary of A, and this is the boundary of B. So basically, you're talking about those two circles. That's the boundary of A union, boundary of B. But the union sets, okay, the union sets, which is this whole thing here, the boundary, however, refers to this guy. That's the boundary of A union B, which is a subset of those two circles. The boundary of the intersections is a subset of the union of boundary of A and boundary of B. There are many other properties that unfortunately I don't think it's that important in this course. That's why I'm skipping this, okay? That's why I'm skipping this. But if you're interested in this, you're welcome to look up all those properties, okay? All those properties. And after this, after we understand the meaning of points and accumulation points of a set in Rn, we can move on to talk about 9.1, which is the limit of sequences in Rn, which is a new segment that I will start next time. Okay, so that's our next topic. All right, and I'll stop here today.